Good morning. This is Steve Hudson with Powermetrix. Thank you for joining us today. We'll be talking about Four Quadrant Metering. For those of you that don't know me, I'm the Vice President of Hardware Engineering here at Technology for Energy Corporation, which is the parent company for Powermetrix. I've been with the company for about 11 years. I'm sure I've probably met several of y'all at meter schools. I know we're missing out on these opportunities this year, but I appreciate that you all came to visit today. This is the latest in our COVID-19 quarantine webinar series. Just want to let you know, again, today we're going to talk about Four Quadrant Metering. We also have another presentation this week on Thursday, which is going to be an ANSI C12 update. I am an active member of ANSI C12, voting member. I've been there since 2012. And really the purpose of the update is to sort of educate those of you that are not familiar with ANSI C12, but also to give you an update about what's going on in the world today, in the world of ANSI. So let's go ahead and hop into our agenda for today. First thing we're going to do is a review of some of the things that we've talked about over the last week, talking about watts, VA, and VAR, how those are used in four quadrant metering. Really want to talk about what is four quadrant metering? Why is that important in the world that we have today? We're going to show some vector diagrams of the four quadrants. That's a common misconception that the four quadrants in four quadrant metering match up with the quadrants that are in vector diagrams. That's actually not the case. So what we're going to do is go through an example of each quadrant and show you what that looks like in the real world, as well as what sort of vector diagram you would expect to see. Next big question, of course, is how do you meter four quadrants? The way that it was done historically is very different than the way that it's done today. And so we're going to talk about both of those. As I mentioned, we will have some actual data from real sites. For quadrant metering, we'll talk about some of the challenges in actually setting up the meter, as well as doing verification of those sites. And so with that being said, let's go ahead and jump into our review of watts, VA, and VAR. Watts, I like to call that useful power. That's the power that's doing real work at a load. It's lighting a light bulb or turning a motor. Historically, over the last 100 years of electricity metering, of course, watts is mainly what we've been interested in metering, because most of the loads, historically speaking, were resistive loads. A resistive load is interesting in that it will allow the current to be in phase with the voltage, thereby producing watts. A lot of the more modern loads that we have are not purely resistive. There's either a capacitive or inductive element to that. As we add more capacitance and inductance to the load, we start to generate a different kind of power, which is the volt amp reactive, or VAR. This is not useful power in that it does not do useful work. It's not lighting something, it's not turning a motor, it's not doing things that we as the consumer ultimately want to pay for. It is real power. It does have to be generated, it does have to be transmitted. And eventually it has to be paid for. It's really just an artifact of the inductance and capacitive in the load. But as such, we as a utility really would like to minimize the amount of VARs and maximize the amount of watts, because of course watts is typically what we're billing for. And then finally VA. VA is the total power in the system. It is the vector sum of the watts and the VARs. A lot of people have the misconception that I can just take the number of watts and the number of VARs and add those together. That's not true in vector math, because there's a direction, a phase angle associated with that. And so it's a little bit more complicated. And so when I say vector sum, keep in mind that that's not just the magnitude, but also the direction, the phase element of that. What we'll see is that VA is ultimately, of course, what the utility is paying for, and we'd like to try and keep our watts as close to VA as possible, once again minimizing the amount of VARs. A useful illustration that you see a lot of times at meter school is this next picture. Either you'll see a keg of beer, or in this case we've got a mason jar. I'm from the South, I'm a Southern Baptist, so what we've got here is a mason jar full of root beer. Illustration is still the same though. Basically, what we're interested in paying for when we get a beer or a root beer is the liquid, and that represents the watts. Once again, that's the useful part of that. The VARs is represented as the foam, which isn't really useful. It is part of the package, but once again, that's not really, we don't want a jug of foam. We really want more liquid than we want foam. So as such, we want to maximize the liquid and minimize the foam. The VA, of course, is the total power, and so that represents the sum of both those two things. And so a good question we want to ask ourselves if we move forward in this is, so where do these VARs come from? I think I mentioned earlier that resistance, of course, produces watts because that puts the current in phase with the voltage. As we start to add inductance to the circuit, that creates more and more VARs. Inductance is a characteristic of the transmission lines, of course, going from the production facility to the end user. And so in this particular picture here, I'm actually showing a picture of Fort Loudon Hydroelectric Dam, which is a 500 megawatt facility that's actually just a few miles from my house. And so depending on the length of the line from, say, the dam to my house, the longer the line, the more resistance, the more inductance you're going to have. The more inductance, of course, is going to add more and more VARs, the more inductance that we have. When we add that inductance, an artifact of that is that the power factor starts to decrease. Power factor, of course, is associated with the phase angle. As we get more and more inductance, what we see is that that phase angle between the voltage and the current grows larger and larger, and so as such, the power factor comes down. If we remember the formula for watts, it's the amplitude of the volts times the amplitude of the current times the cosine of theta, which is also the power factor. And so power factor is quantity that can range anywhere from 1 down to 0. The lower the power factor, the less watts are going to be generated and the more VARs are going to be generated. Once again, we as a utility typically want to maximize the watts because that's what we're being charged for. And so a lot of times what we'll have to do to compensate for that inductance is we can add capacitance. Inductance and capacitance are duals in the realm of electrical engineering, mean that one can cancel the other. Really what we're doing is we're compensating for that phase angle and trying to bring that back to as small a phase angle as possible, as close to being in phase as possible for the voltage and the current. So that's what that is. Talking about four quadrant metering, the four quadrants really are dictated by whether the watts and VARs are being delivered or received. If I go ahead and skip to the next picture, this came directly out of the Meterman's Handbook. And so what you see is you've got your typical XY axis. On the X axis, you have watts. On the Y axis, you have VARs. Of course, we have positive and negative. And so what we're going to do today is we're going to define a positive quantity as a delivered quantity. And that's looking at it from the utility's point of view. So that means that that's the utility delivering power to the customer. On the negative side, we have received power. And so received power would be defined as the customer actually providing power back to the utility. And so here in a little bit, we're going to talk about renewable energy sites because that's typically where you're going to get into a situation where you see received power. And so we'll talk about that more as we go through each of the four quadrants. The other characteristic associated with each quadrant is whether it is inductive or capacitive. Inductive circuits, of course, produce a lagging effect. Lagging meaning that the current lags behind the voltage in time. If I go and I take an oscilloscope and I look at both the voltage and the current waveform, for a purely resistive load, those two are going to be on top of each other. That's good in that gives you a power factor of unity and purely watts coming out of that. As we add inductance, what you see is that the current starts to lag behind, the sine wave starts to shift later in time, and so that phase angle opens up. The phase angle is simply the time difference between the voltage and the current. And so in quadrant 1 for an inductive circuit, we would call that a lagging effect. If we go in the other direction, we add capacitance to the point that we start to lead the current. The current is leading, actually meaning it's ahead in time of the voltage. One very important thing that I want to point out is that if we look at the four quadrants as defined in the Meterman's Handbook, that does not line up with the same four quadrants that you have in a vector diagram. That's a very common misconception that one quadrant maps to another, in terms of phase angle and whatnot. And what we'll see is that as we go through each quadrant, you will see that there is some difference between the quadrant of the four quadrants in the four quadrant metering versus the vector diagram that we're looking at. So let's go ahead and look at quadrant number 1. This is the most common quadrant in that this is the kind of quadrant that we operate in most of the world nowadays. simply because of the fact that it is an inductive load. Most modern loads that we see have some inductive component to them, and so as such there's a little bit of lag to the current. We come over here and look at our vector diagram. What we see, got the mouse? Hold on a second. We're going to set this up so I can actually point to the vectors. There we go. All right, thank you, Jared. So what I want to point out is if we go and we look at our vector diagram, oop, I lost it again. Can you see it? Oh, there it is. Okay, got it. Sorry about that. All right, so if we look at our vector diagram, what we see is there's a phase angle. This is our VA, that's our A phase voltage. This is our A phase current. And so we have a little bit of phase angle between the two. For an inductive load, what happens is that the more inductance we add, the more this current moves in a clockwise direction from the voltage. And so we can get a very good idea from looking at the vector diagram of how much inductance is on that. In this particular load, we've got inductance on each of the three phases. This is probably representative of a 4-wire Y installation. And so we've got probably a three-phase motor. And so as such, we're adding a bit of inductance to that. The thing I wanted to point out is for this particular quadrant, we have both positive watts, delivered watts, and positive VARs. And so once again, that's a very important definition that you're going to see, that the utility is delivering both watts and VARs to the customer for this particular kind of load. If we move to quadrant number 2, we've now gone from an inductive circuit to a capacitive circuit. We've also changed sign on our watts, so we've gone from positive watts to negative watts. So that now means that rather than the utility delivering watts to the customer, the utility is now receiving watts from the customer. And so a good example of that, of course, would be a renewable site, for example, a solar site. This particular quadrant, we still have positive VARs, but we now have capacitive load, which means it's leading the current. And so if we go and look at our vector diagram, what we're going to see is if we go and we look at our A phase voltage, normally what you would expect to see on a bidirectional site with a solar array during the day, if the solar array is generating more power than the consumer needs and they're putting energy back onto the utility, the current arrow would be 180 degrees opposed if it was an ideal purely resistive load. Since this load actually has a capacitive effect, let's say for example we have a capacitor bank on that and we have more capacitance than we have inductance, what you'll see is that you'll actually start to have some phase angle from the 180 degree point. And since it's a leading current, that means it's going to be moving in a counterclockwise direction. And so that's true for each of these three phases, is what we see. If we move to quadrant 3, we still have negative watts, received watts, and so we're still on a renewable site, but we've now gone from a capacitive load to an inductive load. So let's say we go and we put a motor online, and so we basically swamp out that capacitance with enough inductance that our vectors have now moved in the opposite direction. So once again, if you look at the vector diagram, if we start out with the A phase voltage and we look at the A phase current, ideally it'd be 180 degrees for a purely resistive load. Since it's an inductive load, we're going to be moving in a clockwise direction, and so the vector will be moving up this direction. And then finally, quadrant 4, we're back to positive watts, but we still have a capacitive load, so we have negative VARs. And so this could be, for example, a capacitor bank on a system whereby the main load has been removed. So we're still driving the capacitance, but we don't really have enough inductance so that the overall load looks capacitive. The current arrow is back on this side of the vector diagram, but instead of it being down here where we normally expect it for an inductive load, it's moved up in the counterclockwise direction so that we have a phase angle going in this direction. So now that we've gone through the 4 quadrants, we want to ask the question, well, how do we meter that? Well, in the olden days, you really had to have 2 meters. And most of the time, of course, those are going to be watt meters. And so the reason you had 2 meters is that the watts can be either positive or negative. They can either be delivered or received. And so the meter would have to be wired up, one of them being wired up for delivered watts and the other one being wired up for received watts. A problem, of course, with a mechanical meter is a lot of mechanical meters had detents, and so you couldn't use just the one meter because of the fact that the detent would restrict the disc from moving in a negative direction. And so, of course, the way to fix that is I've got 2 meters. If we actually wanted to go and meter the VARs, that could be a problem for the older meters. If you all remember Q-hour meters, those were based on a phase shift. They do a 90-degree phase shift, and so as such, you got sort of an answer, but it wasn't an ideal answer. And so as such, that could pose some problems, certainly if you had both positive and negative VARs, delivered and received VARs, and so that didn't really work very well. The good news for the modern world is that solid-state meters do a really good job of doing four-quadrant metering. Of course, a solid-state meter is based on a digital circuit. It digitizes the voltage, it digitizes the current, turns that into a number that can then be computed using a microprocessor or some other sort of logic device. And so solid-state meters are really ideally set up to be able to do that. That being said, solid-state meters can also be used for what we call net energy metering. Net energy metering is basically where a customer can be credited or paid for excess energy. So if we have a customer that has a large solar array, and during the day, if that solar array is generating more energy than the customer needs, if the utility gives the customer the option, they can put that energy back onto the grid and be credited for that. The amount of credit, the amount that the customer gets paid, is really up to the utility or perhaps the local PUC or government to dictate how much that is. Certain states will limit the amount of excess energy that can be credited to the customer. We actually had one fellow that we knew in the state of Hawaii that had a solar array, and of course Hawaii has a lot of solar energy, and so as such he basically was never having to pay his utility bill. And so the state of Hawaii finally got to the point they're like, hey, you know, net metering isn't working for us. The utility's really losing money here, and so as such they had to basically stop their net metering program where they were paying people. There are other states that have gone and dealt with that simply by just imposing some sort of surcharge, on customers that have bidirectional energy sites. The reason, of course, is that utilities have a lot of overhead. They have a lot of equipment that has to be maintained. And so if everybody has a solar array, everybody's providing their own energy, that becomes a big problem for the utilities. So that being said, net energy has been somewhat of a contentious issue, but we're working through it. Just to give you a very simple example of how net energy works, let's say we've got a customer that consumes 500 kilowatts of energy from the utilities at a rate of 10 cents per kilowatt hour. That works out to be $50 due to the utility. Let's say that the utility will actually pay the customer back for any excess energy at half the normal rate. So we're going to pay you 5 cents per kilowatt hour. And this particular customer has generated an excess of 100 kilowatt hours of energy, which works out to be $5 due back to the customer. So that being said, the net bill is very simple. It's basically the amount the utility is charging the customer minus the amount that the customer would be getting back for the excess energy they put back on the grid. So in this case, $50 minus $5 is $45. As I mentioned, some people can actually generate enough energy so that they essentially have no bill at all, which once again could be a problem for the utility. So this time I actually want to take a little bit of segue and start talking about renewable metering, since that is where most of the time you're going to see four quadrants. Renewable site is simply a site that can generate excess energy that can be put back on the grid. Once again, that's power being received back by the utility. Most of the time, most of these sites were dealt with 2 meters, one for delivery and one for received power. Once again, with solid-state metering, the solid-state meter can do that by itself most of the time. The modern meters can be programmed really to do that any way you want. They can have either 2 registers, one for the received energy, one for the delivered energy. They can have even yet another register for the net, or they can just provide the net as the difference of the 2. So when I say what's a renewable site, what kind of sites do you normally think of when you think about renewable? Well, the big 3 that you see a lot of times are solar, wind, and hydroelectric. I had mentioned to you we have a lot of hydroelectric energy here in Tennessee because we fall under TVA. That's Tennessee Valley Authority, which has several dams. I mentioned Fort Loudon's one that's relatively close to us, but we have over 20 dams in our system. So a lot of our power does come from hydroelectric. If we look at trends, if we talk about statistics first, right now, this is data from 2019 from the Department of Energy. We see that if we look at a pie chart of all the energy being consumed in the United States, about 11% of that is renewable energy. In the last few years, natural gas has come up quite a bit, coal's gone down, but renewable energy is also starting to grow. If we look at the breakdown of that 11%, what we see is the large majority of that is still biomass. Biomass, of course, is where we're burning some sort of combustible. It could be garbage, could be wood, could be other waste to generate energy. Beyond biomass, wind is actually the #1 producer at 24%. Hydroelectric comes in at third place with 22%, and then solar at 9%. If we look at the trends for the future, and this is really what concerns you as the utility is that renewables are gaining a lot of steam. Over the last 5 or 6 years, there have been many incentives put out by the government for solar energy in particular. And so if you look at here at the graph on the right, what you see is that solar energy is actually lagging behind a little bit, but in the next 20 years, it's expected to actually pass wind energy. Wind, there's been a lot of utilities investing in wind, and so there's still a fair amount of rapid growth over the next probably 5 or so years, and then it's going to start to taper off. Solar is going to be fairly consistent because you have both utilities and residential and commercial customers that are investing in that. And so that's one reason why Four Quadrant Energy is so important to utilities, because as we see more and more of these sites coming online, it'll be important for you as the utility to understand what the four quadrants are and how that metering is properly done. So in summary, with renewable sites, once again, right now we've got about 10-11% of our total energy being given by renewable sites. Solar and wind will continue to be the largest growing segments in the United States and will become a majority of the new renewable sites. The estimates are that both of those segments, both solar and wind, should double their output in the next 5 years. And so the last thing I wanted to cover today was to actually talk about some sites that we've been out to visit. Just to talk about, what are those sites, how are those sites metered, and how are those sites tested. So here in Knoxville, Tennessee, we have a 1 megawatt solar farm out in East Knoxville that's made up of 4,600 panels. This was built back in 2010, so they've had this in operation for about 10 years. This is a privately owned site, purely for the purpose of generating electricity and selling it back to our local utility, KUB. Another part of the site, we've got 4 large DC to AC inverters. Of course, solar energy comes out as DC. Most solar cells are outputting somewhere in the tens of volts and up to several amps, depending on the size of the grid. Those can either be put in series or parallel, which can then be fed into a DC to AC inverter that will convert that from a DC voltage into an AC sinusoid. That then has to be put through a transformer and put back on the grid. You see over here, these are the inverters. This is a large 8.4 kV transformer to put that back up on the grid. So how is this site metered? Well, interestingly enough, it's only a single meter. We've got a 9S meter set up as a 4-wire Y installation. It is set up, of course, for bidirectional metering. But what we'll see here in a second is the vector diagram doesn't necessarily look like what you might expect. In addition to the meter, of course, we have some 205 CTs and 71 PTs to be able to step that down. So if we go ahead and we do a site analysis, one of the first things we want to look at is the vector diagram. Vector diagram is one of the most useful tools that you have in your toolkit because it gives you a lot of information very quickly. Now, based on my education with a solar site, what I normally expected to see when I looked at the vector diagram is if you're out at the solar site and it's the middle of the day and you're generating lots and lots of electricity and you've got more electricity than you need, i.e. you're putting energy back on the grid to the utility, you would normally expect the current arrow to be pointing in the opposite direction. For this particular site, that's not the case. This meter was actually set up so that positive energy flow is from the solar array to the utility. So it's sort of opposite what you would normally expect until you think about, well, this site is only for the production of energy. This site is really never set up to consume energy from the utility. And so that being the case, it made more sense to the utility to say, hey, I'm just going to set this up so that the solar array is the utility and the utility is the customer. And so, looking at the vector diagram, the current vectors are going to be closely aligned with the voltage vectors, and that means that, hey, we are generating energy and we are delivering it to our customer, which in this case is the utility. The other thing I'd like to point out is that these current vectors are actually leading, and so what that means is we've got a fair amount of capacitance on this array, and so that would actually be in the fourth quadrant from the four quadrants that we talked about earlier. This was a somewhat cloudy day. They were still generating about 0.5 megawatt of energy, so there was a fair amount of energy coming out of this system. If we go and we look at the waveform display, this is another important part of renewable energies, about solar sites in particular. The fact that you have to do a DC to AC inversion means that there are harmonics that are going to be generated. Now, harmonic energy, those of you familiar with harmonics know that harmonics are multiples of the fundamental frequency. Fundamental frequency in the United States is 60 hertz. And so a second harmonic, for example, would be 120 hertz, third harmonic would be 180 hertz. Harmonic energy is typically not your friend in the sense that it's not, once again, doing useful work. Most harmonic energy is being given up as heat. And so for the utility, that's not a good thing because hot equipment wears out faster than equipment that's not hot. And so harmonics, if it's generating lots of heat, means that over time, you're going to see more maintenance costs going into replacing transformers, meters, other equipment as it runs hot because of those harmonics. And so it really behooves the utility and ultimately the customer to try and reduce that harmonic energy as much as possible. On this particular site, we actually had a really good inverter because of the fact that you'll see these are the current waveforms here, the darker waveforms. You'll see the 60 hertz fundamental, but you'll see a higher frequency riding on top of that. From doing a harmonic analysis, what we found was that most of these harmonics were at the 70th harmonic or above. For most meters, that doesn't even register. The meter can be set up, depending on the quality of the meter, sampling rate of the meter, to do that, but really most of that energy is really not going to affect the meter. And so what that means is the meter should have no problem metering this site. If it's a good bidirectional meter, four quadrant meter, once again, it's a little bit of capacitive load, so it should be able to meter that without any problem. So if we go and we run a meter registration test, what we find is that, hey, this test looks really good. This meter is working just near perfect, 99.99%. You will note that the VARs are negative. Once again, that's indicative that there's some VARs being put back on the grid, but that's okay. As part of a transformer rated site, it's important that certainly that we test our instrument transformers as well. You definitely want to test your CTs. I want to try and test your PTs if you have the opportunity. But the thing to pay attention here, of course, is once again, how's the meter wired? In other words, you have to be careful of the polarity. Make sure that the polarity of your high voltage current probe is pointing in the right direction. Otherwise, you'll get a phase error when you run your CT test. And so here's a picture of the results. Once again, excellent results. Those were 205 CTs, and so we have very low ratio errors. The phases are actually also quite good. So this site was remarkably good when we ran through that. One of the other things that Powermetrix recommends when you're out at a transformer rated site is that you should also check your burden. Burden, of course, is the amount of resistance being put on the secondary side of your current transformers. Current transformer, when it's selected, of course, has an accuracy at a given burden. If you exceed that burden, the accuracy of the CT will start to go down. Not only will it go down, it will also go against the utility. It'll go in the customer's favor. And so that means that the utility is losing money because of that inaccuracy. And so one of the features that we offer on our 3 series analyzer is what we call our direct burden measurement. The way that works is that it basically measures the voltage and the current and uses good old Ohm's law to be able to figure out what the direct resistance is on the secondary. If you remember, Ohm's law, of course, is voltage equals current times the resistance, V equals IR. If we take that equation and turn it around so that we want resistance, resistance is equal to the voltage divided by the current. And so if I can measure the voltage on the secondary of the transformer and the current, I can just divide voltage by current and poof, I get the burden. And so for this particular site, we have somewhere between about 0.1 and 0.2 ohms. These transformers are big enough so that probably shouldn't be a problem. It's very consistent. A lot of times on sites, transformer rated sites, you may have loose connections. Loose connections are one of your biggest enemies in terms of adding extra burden. It doesn't take a lot of extra resistance to get beyond the burden rating of that CT. And that could be something as simple as a connection that's come loose over time, perhaps a loose test switch. Once again, the direct burden measurement can help you find those loose connections and that extra burden that can, once again, result in loss of accuracy and loss of revenue for the utility. So if we move on to case study number 2, this is the Gila River photovoltaic power plant, which is actually mounted on top of the Huhucom Hospital in Secaucus, Arizona. 87 kilowatt array, and so during the day, of course, in Arizona, you get a lot of solar energy. It does a good job of trying to reduce their bill. If we go and look at the vector diagram, hey, this looks more like what I expected. We actually have our current vectors pointing about 180 degrees out from the voltage vectors. And so what that means is that this site is generating excess energy. It's a hospital, of course, and the hospital is open 24 hours, and so that means during the day they generate enough electricity that they can actually put some electricity back on the grid. At night, of course, they're not going to have any solar energy, and so they're going to have to pull. And so what you would expect is this vector diagram will change between the day and the night. One issue with this particular array was that the inverter was not quite as good a quality as that first one that we saw. And so what that means is that there's a lot more harmonic content. The dark waveform here, once again, is the current. The thin waveform is the voltage. It looks pretty clean. We measured a THD of 2%. THD, by the way, is total harmonic distortion. That's a measurement of the amount of harmonic energy that you have on the system. We'd like to keep the THD as low as possible, simply because, once again, harmonic energy typically isn't doing useful work, and we'd like to minimize that as much as possible. This particular system had a current THD of between 50 and 60%, which is pretty high. What you see is that it's not very sinusoidal. There's a lot of squareness to that. Less expensive inverters are typically square wave inverters, and so it'll generate a waveform that looks more square. Square waves have a lot of harmonics, and so once again, that's something that energy is being burned up as heat and probably not doing the customer or the utility any favors. Third site we're going to look at is also in the state of Arizona. This is a U-Haul facility that had a large solar array mounted on top of it. This was a 4S meter, so you had a 3-wire system. Right now, this is during the day, and so once again, what you see is that you've got your current vectors 180 degrees out from what you would normally expect. You'll notice down here, if we look at our watt hours, it's being represented as negative because of the fact that we are, the utility is receiving energy back from the customer. Important point about the meter test, the meter registration was minus 100.9%. Now that minus sign is simply because of the fact that, hey, the meter is running what in olden terms would have been backwards, but it's still registering properly. The reason it's 0.9% is we're using clamp-ons on this particular site, and so the clamp-ons are a little bit less accurate, but that's still a good reading for that particular meter. But the main thing I wanted to point out was that negative sign, once again, is just a clue that this is a bidirectional site and that you've got current being received by the utility rather than delivered to the customer. This is the same site at night, and so what happened was the vectors turned back around to the quote-unquote normal direction. So you've got positive watts now. You see that down here in your power data, that we've gone from negative watts to positive watts. We went and retested the meter. It is important to test the meter going in both directions so that you know you're getting good registration. We got 100 plus 100.15%, and so basically we've checked the meter in both directions, and so that's a good thing, just to make sure it's doing its job. Once again, if we do a harmonic analysis, what we'll see here is that the voltage THD is pretty low, less than 3%. Current THD is about 17%. That's not terribly bad. You see a lot of third harmonics simply by the fact that, it's a square wave inverter. Square wave is made up of an infinite number of odd harmonics, and so this is, once again, representative that I've got a square wave inverter doing my DC to AC inversion. So in summary, with the renewable sites, first rule is that you should test for energy flow in both directions. Make sure that it's working both positive and negative. Now, of course, most folks aren't going to stick around till nighttime to test the meter. So an easy way to do that is, of course, use a load box. Most modern load boxes can be programmed so that they can look like delivered or received loads, and so that makes it very easy for the meterman to be able to check that. Another useful part of a load box is that if the site's not generating power, you can go and plug in directly and add phantom load to that system, thereby being able to test the system much quicker. Our 335 product is a very good example of that. It has a 5 amp load box, which is programmable for both either delivered or received energy. And then finally, of course, for the renewable site, transformer rated site, be sure to check your CTs and your PTs. The meter is only as good as the information that comes to it. As we like to say in the electrical engineering world, garbage in, garbage out. So if your CTs are wired up improperly, even that meter is registering 100%, if you've got a backwards CT, you're losing money. And so be sure and check that. So once again, in summary of the overall presentation, Four Quadrant energy, Four Quadrant metering is very important. It's going to become more important because we've got a lot more wind and solar sites being installed over the next 6 to 20 years. Four Quadrant energy metering is required for bidirectional energy sites. Be sure and always check your energy flow in both directions, folks. Make sure it's working both ways. So that being said, that's our presentation for today. Once again, thank you all for tuning in. If you have any questions, by all means, please send those to Mr. Mullins. We'd be glad to answer any questions you have, either online or offline. And we just appreciate your time. I'm sorry, before I log off, also we have, just a reminder, on Thursday, we will have our ANSI C12 update. Once again, tune in 11 o'clock Eastern Daylight Savings Time.